Okay, good evening everyone. We will start with an extra example on using ABAQUS for unsymmetrical sections, cantilever beams. Um, Last week we talked about these sections, and this week we will talk a bit about unsymmetric section. The aim actually of this tutorial is to know how to define different thickness for different walls of the section. So that's the main aim for this tutorial. So we have a thin wall section, cantilever beam. The length is 1.2 meter. We have a point load is 5 kilonewton. As you see, this is a unsymmetric section. You have the length of the top flange about 150. It's a 150, and bottom flange is 90 millimeter, and the height is 170 millimeter. The top and the bottom flange has the same thickness, and the web have the thickness of 5 millimeter. What you have to do, you have to use each noted shell element, and you have to use the mesh configuration used here. So in the top flange you have 4 elements divided by 4 elements, and the bottom flange is 3 elements, and over the web you have 1, 2, 3, 4 elements. And on the axis, in the axial axis, longitudinal axis, you have 10 elements. What you're supposed to do is you need to find the deflection over AB. You need to find the bending stress S11 over AB also. You need to find the bending stress over RS, RP and QP. You need to find the shear stresses over also these elements, these lines, and then find the shear flow over these lines. So that is going to be used, of course, finite element analysis ABAQUS. To start, we will open ABAQUS, and then I will start with standards explicit model. Let's go with the B part. With the part, now you click on the part, and then you click on the create part. Let's call it as a beam. It's a 3D and shell, and I will do extrusion. And the extrusion, I will draw the section and then extrude it in extrude it over the length. And then let's continue. Let's move this into the side. Now, assume that x and y is on this corner here. This is an x and this is y. So let's draw firstly this point before. Let's draw this point here over here. The coordinate of this point is this. We're just going to zoom it in. The coordinate of this point here is 90, 0. And then the coordinate of this point is 0, 0. The coordinate of this point is 0, 170. And finally the coordinate of this point is 150 and 70. So that is if we assume the coordinate system is this x and this y here over. So let's do it. Now we click on create lines connected. The first point we said it is 50, 0. I think it's 50, 0. No, sorry, 90, 0. 90, 0. Enter. And then 0, 0. Enter. So we create this line. And then on the up is it's 0, 170. And then finally 150, 170. So if you click on auto fit view, you get this section. Now you need to cancel procedure and say done. That will show you that you've done the section. Now you need to extrude it. With extrusion, value or the depth value is gonna be the length of the beam, which is 1200. Then okay. Now we created a beam section. Now if you want to rotate it, you use the rotate view, and then you keep rotating to check that is okay, that is fine. Now then we go to Material Property. With a property here, you need to use Material Manager and then create. So it's a steel element or steel material, and you have mechanical elasticity elastic. The Young modulus is 200,000 with Newton per millimeter squared and 0.25. Now this is done. Now you dismiss. Now you finish creating material. Now you create the sections. Now you say create. The section is, now we need to create two sections. One actually for the flange, top flange and bottom flange, which has the same thickness, and one here actually for the web. Now let's create a section for flange section. Flange section. It is a shell, homogeneous material, and then continue. The thickness of the flange is 5. Sorry, it is 2, as it's shown in the figure here. It is 2. So you continue. You said okay. Now let's create another section for the web. So create the web section, and we continue. The thickness of the web is 5, as we saw it here, and then okay. Now we create two sections, one for the flange and one for the web. Now we need to assign this section into that beam. So let's dismiss it, and we go to section assignment manager, and then we create an assignment manager. Then we can ask what is select the region to be assigned a section. So let's click in the top flange, and we need the bottom flange. So in order to multiple selection, allow for multiple selection, we click shift on the keyboard, and then we click that with two flanges, and then the OK. Now the section we need to choose either flange section or web section, of course the flange section, and we keep the default as it is, and we said OK. Now we ask you another region. Yes, we click on the web, and then you said OK, and then you need to choose web section. After you choose web section, you said OK. You notice that you created two named sections, one for the flange and one for the web. Now let's cancel procedure here, because we finished selecting the shell, the beam the beam walls, and then cancel procedure and dismiss. We've missed one important step, which is set directory. So let's set the directory. So we go to file, set directory here, work directory. I will set work directory on, let's say, ND. I would do ABAQUS, for example, ABAQUS tutorial, and then he said okay. So I will save all my documents in ABAQUS tutorial folder, and then he said okay. So and then he said okay, so everything will be fine now. Now after that, let's go and save. It will automatically will be saved here, so we'll see it unsymmetric beam section, and said okay. Now let's go to assembly. So you notice that the beam is not there, so we're gonna bring the beam into our attention, our model. So we saw assembly, create a assembly or instance, and we choose independent in order to mesh it on the section on the instance, and then okay. Now we go to step. We need a step actually to assign the load into as a step load, and then you go into step manager. You say create, and then we continue. We choose a static general, continue. We keep everything as it is, as a default, and then okay. Now let's dismiss. Now let's go to the load. At the load, we need to apply a boundary condition here on the end. So let's go into boundary condition manager, and then you say create, and this is called boundary condition fixed. Let's call it fixed boundary condition. Let's choose displacement rotation, and then continue. Let's click on this edge, on this line, and then shift on the keyboard, this line and this line. So it's just all highlighted, and then done. Take all this rotation, this degree of freedoms. You have 3 displacement and 3 rotations are all zeros, which represent fixed boundary conditions, and then okay. Let's dismiss that. Now I need to apply a load at the tip at this point here over the web, and then we will go to load manager, and then we'll create, let's call it loading, and then I will choose concentrated force, and then continue, and click on the base point, and say done. Now what you have, CF1 represent the load in the X direction, CF2 in the Y direction, and CF3 is in the Z direction. Now we have vertical load in Y direction, which goes downward, so it will be minus 5,000, which 5,000 is in Newton. Then okay. You will see the arrow here. Confirm you are doing it correctly. Then you go to mesh. Let's save it. Now what you have 4 elements here, 3 elements here, this flange, and 4 elements in the web. So let's do that. You need to click seed edge, click on this line, shift on your keyboard, click on this line, and say done, by number, and set 4, and okay. And then again click on this line, shift on your keyboard, shift in this line, and then done. The number of elements is 3, as it's shown actually in the figure. He show you have 3 elements, here you have 4 elements, and then okay. Now you need to find for the web, which is in the web we have 4 elements. And click here. Now you will have difficulties to find the other side of the web of the line, so let's zoom it in. Here we go. You know, to zoom actually you need to use the mouse wheel, and then go to the shift and click here, and saying done. You have 4 elements, and saying okay. Lastly, as you see here, we have over the length of the beam, you have 10 elements division. So you need to divide on 10 elements. So again, make a window over the whole beam here in the middle somewhere. You will see these lines or in Z direction will be highlighted and send on. Use for 10 element. Then OK. And then done. Click on the part mesh part instance and then say yes. So that is your model is meshed. Now you need to choose the element type. What type of element is it? So you click on element type and click not only on this or this or this. You need all the elements. So you get a window. So all the beam, all the sections, all the walls. So it's done. It's a quadratic. So I'm going to use SR8, which is required. Which is 8 noded shell element. And then OK. Then you said OK, done. After that, you can create a job, and then you go to job manager, create, continue, OK, and then you submit and wait for the result. Look at the result. If you click here, you will find a deformed shape. That is your deformed shape. And this is, you notice actually that the deformed shape is where, and it's simply what you really have, which is interesting, is because it's non-symmetric and you have the load applied in a symmetric center, so you will end up with something like this. Anyway, let's go to find the deflection over AB, vertical deflection. So you go to U and then U2, that's what you are looking for. And then go to tools, XY data, tools, path, manager. Create, let's call it A, B. And then continue, add after. I'm gonna start node by node. Zoom in. Done, and then say OK, and then go to tools, XY data, manager, and then you say OK, create, say path, you continue, I need undeformed, and you need the distance in the path AB in the distance Z, and save as, and said OK. With your double click will give you the displacement over the AB. That's done. By the way, you can plot it, and you notice displacement is not a straight line, of course. Now, the second thing you need to find the Bendix is over AB. Now what you can do, you go into S and S11. Bring back this XY data path, and you will find out that S11 will be as an output, and then save as, and OK. If you double click, what do you notice? You will notice that for each case you have, for each distance you have two values, and this is, so let's explain the reason behind it. So let's close XY data from path. If you go into query information, node prop value, now choose to, instead of element, choose it to nodes. Now click, not to click, choose one of these. What do you notice? You notice you have 4 values, and these 4 values came actually from 4 elements attached. From 2 elements come 2 values for the element 1 and 2 here at the top with the flanges, and 2 values from the web. Again the same here, you will have 2 values, one from the flange and one for the web. Now what you have to do, over AB choose the maximum values, and this maximum value represents the bending moment over AB for the web. So in this way you need to choose 171.059. Okay, now close this and back to this point here. So what you have to choose, at 0 you need to take 171, you delete this because 171 represents the bending moment, bending stress at the web, which is the maximum at the joints here. You take, at 60 you take 155, at 120 you take 142, and 180 you take 173, and you continue. At the last you take 9.5 at the maximum. So you take the maximum value of the bending for each representative, and then OK. Now you need to find the bending stress over this RS, RB, PQ. So SR or RS, this is RS, RP, RQ, PQ. So let's create passes, which is at the middle of the beam. So it is gonna be here. Now let's create path. So create, and we are gonna call it SR. Continue. It is very deformed, so I would do the following. So I would make plot undeformed shape, so that's easier to read now, and then we'll look at the middle, and the middle line is this one. Oh, sorry, this one. This middle line. So after, and there we go. This. and then say done, and then okay. That is your SR. Now I need RP. Sorry, let's do QP. Let's do QP now. Create QP, continue, and add after. Sorry, this one. Yeah. So QP, yes, right. And then done. So okay. And last one is RP. Create RP, continue, add after. So this is your RP now, here. So this is your RP. Zoom it in from below to top. RP over the web. And then done, and then okay. Now let's find the bending moment over these lines. Then you go create to X data manager, create path. Now bending moment is 1 over first one is SR, and the SR is in X direction, and this is 1 and then save as, and okay. Double click, you will have all value for the bending over here. Now it's okay. And if you want to take SR and then you take QP, so you go to QP and then XY distance, because this is the path in XY, and then save as, and okay. Double click, you will end up with the bending stress is 1 over these distances, and this distance is taken from this line here. Then okay. And lastly, over the web you need RP, and this is your RP, and it is the distance is over Y distance, because this is over Y distance, this path is over Y distance, and save as. Okay, double click, you will get your bending stress over the web. That's done. Now I need to look at shear stress over these lines. So let's go to S11. So let's go this web RP, the shear stress over RP. This is a change, and RP is over Y direction, and then save as, and okay. By double click, you will give you the shear stress over RP. Remember, this is this value at the start here 17.18 and end is 16.79. So 17.18 at this point here for the web, and 16.79 at the end here at the web. Then okay. Let's take the shear over G, and this is the shear stress in order to find the shear flow, you need to multiply the shear stress by the thickness of the web, which is 5. So you multiply this value by 5 to give you the shear stress, shear flow. Okay, you go to finally SR, and then it says path is over X direction, and save as, and okay. Double click, it will give you the shear stress over this distance here, which is start from this edge. These are the shear stresses, but you multiply by the thickness of the flange, which is 2 millimeter, and you get your shear flow, and then okay. Finally, you need the shear stress over PQ, and that is your PQ or QP, and QP is in X direction, and then save as. Okay, double click, you will have the shear stresses over here, and you have to do is to multiply it by 2 to get the shear flow. That's okay. Now it is done. So I hope this is useful for the assignment, which is due to in November. Have a nice evening. Thank you.